on a clear autumn night, you can see it with your naked eye. That smudge contains 1 trillion stars, billions of potentially habitable planets, and possibly millions of alien civilizations wondering if they are alone. It is our nearest major galactic neighbor, and we will never, ever reach it. Not in 1,000 years, not in 1,000,000. The laws of physics have constructed an invisible prison around humanity, so vast and so absolute that even traveling at the speed of light, you would need 2.5 million years to cross the gap. But that is not the worst part. The real reason we cannot reach Andromeda is far more disturbing than mere distance. It breaks everything we thought we knew about travel, time, and the nature of reality itself. If you enjoy this kind of cosmic exploration, tap like and subscribe. It helps us more than you know. Now, get yourself comfortable. Let's begin. One trillion stars. Human minds cannot grasp quantities so vast. If you started counting Andromeda's stars at a rate of 1 per second, without stopping to sleep, eat, breathe, or rest, you would finish counting after 31,700 years. You would need to begin your count during the last ice age, when mammoths still roamed the frozen plains, when human civilization had not yet invented agriculture. You would count through the rise of Mesopotamia, the building of the pyramids, the fall of Rome, the Renaissance, the Industrial Revolution, 2 world wars, the space age, and countless generations yet to come. And still you would not be finished. And the light you see when you look at Andromeda tonight? It left that galaxy 2.5 million years ago, when our ancestors had not yet learned to create fire, when the human brain was still millions of years away from developing language or art, or the capacity to wonder about distant galaxies. Those ancient photons have been traveling through the cosmic void ever since, crossing emptiness so profound that human vocabulary lacks words to describe it. This distance defies human comprehension in ways that should disturb anyone who contemplates it seriously. Our brains evolved to understand distances we could walk in a day, or perhaps a few weeks of travel. We developed intuitions about spaces we could cross on foot, territories we could claim with our eyes, horizons we could reach before sunset. The savanna that shaped human cognition measured perhaps 100 miles in any direction. Our ancestors needed to understand where predators lurked, where water sources flowed, where fruit trees grew. Nothing in our evolutionary history prepared us to grasp distances measured in millions of light years. Let me try to make this comprehensible. Though I warn you, the attempt may only deepen your sense of cosmic vertigo. A single light year measures approximately 6 trillion miles. Written out completely, that number looks like this: 6 million miles. Light itself, the fastest thing in the universe, the absolute speed limit imposed by the laws of physics, requires an entire year to travel this distance. A beam of light can circle Earth 7 times in a single second. It can reach the moon in just over 1 second. It crosses the gulf between Earth and the Sun in about 8 minutes. Yet even travelling at this incomprehensible velocity, light needs a full year to traverse just 1 light year of cosmic space. Our nearest stellar neighbour, Proxima Centauri, sits 4.2 light-years away. This red dwarf star represents the closest possible destination beyond our own solar system. At the speed of the fastest spacecraft ever built by humans, reaching Proxima Centauri would require over 70,000 years. 70,000 years ago, anatomically modern humans were just beginning to migrate out of Africa. The entire history of human civilization, every empire that rose and fell, every war that was fought, every book that was written, every song that was sung, would fit many times over into the journey time to our nearest stellar neighbour. Now, multiply that distance by 600,000. Andromeda lies 2.5 million light-years from Earth. Written out completely, this distance equals 15 million trillion miles, 15 followed by 18 zeros. If you could somehow drive a car at highway speeds toward Andromeda, without stopping for fuel, rest, or mechanical failure, the journey would require 40 trillion years. The universe itself is only 13.8 billion years old. You would need to travel for nearly 3,000 times longer than the entire history of the cosmos just to arrive at our nearest major galactic neighbor. But raw numbers, no matter how many zeros they contain, fail to convey the true horror of this distance. They slide off the human mind like water off glass, too large to find purchase in our evolved intuitions. Let me try a different approach. Imagine shrinking the entire solar system until the sun becomes a basketball sitting in the center of a gymnasium. That grain of sand holds everything humanity has ever known, every person who ever lived, every city ever built, every dream ever dreamed. Jupiter, the giant of our solar system, would be a marble sitting 130 feet from the basketball sun. Neptune, the outermost major planet, that frozen world of howling winds and methane seas, would sit roughly half a mile from the gymnasium. At this same scale, where our entire solar system fits inside a small neighborhood, where the sun shrinks to something you could hold in your hands, where would the nearest star be? Another basketball, located in Australia. If you stood in New York holding the basketball sun, the nearest star would be another basketball sitting in Sydney, 12,000 miles away across the Pacific Ocean. The space between those two basketballs would contain essentially nothing. No matter, no light, no sound. Just emptiness stretching across continents and oceans at a scale where our entire solar system fits inside a single building. And Andromeda? This scale, where stars become basketballs separated by oceans, where our solar system shrinks to the size of a gymnasium. The Andromeda galaxy would sit beyond the orbit of Mars around the real Sun. We have shrunk our cosmic neighborhood by factors that dwarf human imagination, and Andromeda still ends up more than 50 million miles away. The nearest major galaxy to our own lies so far distant that even at scales where stars become handheld objects, the gap between us remains astronomical. The emptiness between galaxies exceeds anything most people have ever contemplated. Intergalactic space contains approximately 1 atom per cubic meter, one single hydrogen atom floating alone in a space the size of a small room. Compare this to Earth's atmosphere, which contains about 25 trillion molecules per cubic meter. The air you breathe right now contains more particles in a single lungful than you would find in cubic miles of intergalactic void. Intergalactic space is so empty that it approaches the theoretical minimum of nothingness possible in our universe. Even the best vacuum chambers humans can create on Earth contain trillions more particles than the average cubic meter of space between galaxies. The void between the Milky Way and Andromeda represents emptiness more profound than any human technology can generate. This void stretches for 2.5 million light-years, with essentially nothing in between. No stars to refuel at, no planets to rest upon, no matter to interact with, no cosmic oases where weary travelers might pause to repair their ships or replenish their supplies. Just absolute emptiness, extending in every direction for distances that dwarf not just human imagination but human existence itself. Scientists have confirmed that approximately 50 small dwarf galaxies orbit in the space between us and Andromeda. Like cosmic stepping stones scattered across the void, these tiny galactic systems contain millions or billions of stars each, specks of light in the intergalactic darkness. But even these intermediate galaxies lie hundreds of thousands of light-years apart from each other. They offer no meaningful waypoints for any conceivable journey, no rescue stations for ships in distress, no harbors where travelers might wait out cosmic storms. The stepping stones are so widely scattered that you would exhaust your resources crossing to the first one, let alone continuing to the next. The distance to Andromeda creates a communication barrier as profound as the travel barrier. Imagine for a moment that an alien civilization exists somewhere in Andromeda, orbiting one of its trillion stars. Imagine they developed radio technology 1 million years before humans discovered fire. Imagine they detected Earth somehow, perhaps through observations of our sun's spectrum or our planet's atmospheric composition. Imagine they decided to send us a message. They build the most powerful radio transmitter their technology allows. A beacon blazing across the intergalactic void with more energy than our sun produces in a year. They point it precisely toward our galaxy, toward our little spiral arm, toward our unremarkable yellow star. They begin broadcasting a greeting, perhaps a mathematical sequence that any technological civilization would recognize as artificial, a cosmic hello echoing through the emptiness. That message, traveling at the speed of light, the absolute fastest any information can move through our universe, would require 2.5 million years to reach Earth. 2.5 million years of traveling through darkness, crossing voids where nothing exists, racing at 186,000 miles per second through emptiness so complete that the message would encounter essentially no obstacles along the way. If they sent their greeting when the light we see tonight left Andromeda, that message would arrive roughly now, in our current century. But any response we send would take another 2.5 million years to return to them. A simple exchange of greetings, a cosmic hello and a hello back, would require 5 million years. By the time our response arrived at Andromeda, the alien civilization that sent the original message would have existed for so inconceivably long that they might have evolved into something completely unrecognizable. They might have transformed themselves into digital beings, uploaded their consciousness into vast computer networks. They might have spread across their entire galaxy, inhabiting millions of worlds. They might have gone extinct, their cities crumbled to dust, their planets sterilized by their dying sun. They might have transcended physical existence entirely, becoming something our minds lack the capacity to imagine. The individuals who composed and sent the original message would be gone, of course, dead for millions of years before our reply began its journey. Their language would have changed beyond recognition. Their culture would have transformed through thousands of civilizational cycles. The beings who received our response, if any beings remained to receive it, would read our words as archaeological curiosities, messages from a primitive species in a distant galaxy, responding to communications sent by their own unimaginably ancient ancestors. This communication delay reveals something profound and disturbing about cosmic isolation. Even if advanced civilizations exist throughout both galaxies, even if billions of intelligent species have arisen on billions of worlds, they can never have meaningful conversations. The light barrier creates absolute loneliness across intergalactic distances. Each galaxy evolves in cosmic solitude, forever wondering about neighbors they can observe but never contact, forever separated by gulfs too vast for any signal to cross within relevant timescales. But the distance itself represents only the first barrier preventing humanity from reaching Andromeda. The true prison walls are constructed from something far more fundamental than mere empty space. The distance horrifies us because we can comprehend it, however dimly. What comes next defies comprehension entirely. Consider what traveling to Andromeda would actually require in practical terms. Forget about the philosophical implications for a moment. Forget about the cosmic loneliness and the communication barriers. Focus purely on the engineering challenge of crossing 2.5 million light-years of void. The fastest object ever built by humans is the Parker Solar Probe, a spacecraft designed to study the Sun by diving closer to its surface than any previous mission. During its closest approaches, when the Sun's gravity accelerates the probe to maximum velocity, it achieves speeds of approximately 430,000 miles per hour. This velocity represents an extraordinary engineering achievement, faster than any previous human creation, faster than bullets or rockets or anything else our species has ever launched into the cosmos. At this speed, the fastest humanity has ever achieved, reaching Andromeda would require approximately 4 trillion years. Let me be absolutely clear about what that timescale means. 4 trillion years ago, the universe had not yet experienced its first second of existence. The Big Bang itself, the cosmic explosion that created space and time and matter and energy, occurred only 13.8 billion years ago. Reaching Andromeda at our current fastest speeds would require waiting for roughly 290 times longer than the entire history of the cosmos. The universe would need to live through its entire lifespan from the Big Bang to the present moment, then repeat that entire cosmic history 290 times over before your spacecraft would arrive at Andromeda. Every star that currently exists would have burned out billions of years before you reach the halfway point. Every galaxy would have exhausted its supply of hydrogen fuel. The cosmos would have gone dark and cold, drifting toward heat death, while your vessel was still crossing the intergalactic void. Even if humanity somehow survived and maintained continuous progress for this inconceivable duration, the sun would burn out after about 5 billion years. Earth would become uninhabitable long before that, scorched by the sun's expansion into a red giant, then frozen as the stellar furnace sputtered and died. Our entire solar system would have transformed beyond recognition, while the spacecraft was still less than 1% of the way to its destination. The Voyager 1 spacecraft, launched in 1977, has traveled farther from Earth than any other human-made object. This remarkable machine has been flying continuously for more than 4 decades, carrying its golden record of human sounds and images into the cosmic darkness. After 46 years of continuous travel, Voyager has covered approximately 14 billion miles. This sounds impressive until you realize that Andromeda lies more than 15 million trillion miles away. Voyager has traveled 1/billionth of the distance to Andromeda in 46 years of continuous flight. If Voyager's journey so far represented a single step on a walking path, it would need to take 1 billion more steps to reach Andromeda. At Voyager's current speed of approximately 38,000 miles per hour, reaching our neighboring galaxy would require over 44 trillion years. The mathematics does not care about human ambition or technological optimism. The numbers simply state, with cold precision, that conventional spacecraft cannot cross intergalactic distances within any meaningful time frame. You can argue with politicians, debate with philosophers, negotiate with opponents. You cannot argue with arithmetic. The distances involved exceed our capabilities by factors so large that incremental improvements become meaningless. This realization forces us to consider more exotic propulsion methods. What if we could somehow accelerate spacecraft to velocities approaching a significant fraction of the speed of light? The laws of physics permit objects with mass to approach light speed, though never reach or exceed it. What if brilliant engineers designed propulsion systems capable of achieving 90% of light speed? What then? At 90% of light speed, approximately 600 million miles per hour, reaching Andromeda would require approximately 2.78 million years. This represents an enormous improvement over conventional propulsion. Instead of 4 trillion years, the journey would take less than 3 million. Progress, except 3 million years, still exceeds human civilization's entire existence by factors of thousands. Modern humans have existed for roughly 300,000 years. All of recorded history, from the first clay tablets in Mesopotamia to this very moment, spans only about 5,000 years. Reaching Andromeda at 90% of light speed would require waiting for more than 500 times longer than humans have existed as a species. No government, no institution, no corporation, no civilization could maintain a coherent mission across such timescales. The journey duration exceeds not just human lifespans, but the lifespan of human civilization itself. Languages change beyond recognition over mere centuries. English speakers cannot read text written 1,000 years ago without specialized training. Any civilization recognizable as continuous with our own would have vanished long before the spacecraft reached even the first quarter of its journey. Any spacecraft launched toward Andromeda would travel for so long that the civilization that built it would have risen, flourished, transformed, declined, collapsed, been forgotten, and crumbled to archaeological dust millions of years before arrival. The beings who finally reached Andromeda, if any beings remained aboard, would share no meaningful connection with the humans who launched the mission. This creates what scientists call the generation ship problem. Proponents of interstellar travel sometimes suggest that spacecraft carrying entire communities could travel between stars, with each generation passing the mission to the next. Parents would raise children who would raise their own children, maintaining some form of continuity across the decades or centuries required to reach nearby star systems. This solution might work for relatively short journeys to stars within a few dozen light-years. It becomes absurd for intergalactic travel. A generation ship traveling to Andromeda would require not hundreds of generations, but millions of them. If we assume 20 years per generation, the journey would span roughly 139,000 generations of human beings. 139,000 separate cohorts of people living, reproducing, and dying aboard a vessel, crossing the intergalactic void. Consider what would happen to a human population isolated aboard a spacecraft for 2.5 million years. Evolution operates on timescales of hundreds of thousands to millions of years. Over the journey duration, natural selection would reshape the travelers into something biologically unrecognizable as human. Their descendants would adapt to shipboard life in ways we cannot predict. They might develop different body plans suited to artificial gravity. Their immune systems would adapt to shipboard microbiomes. Their brains might change to cope with the psychological challenges of eternal confinement. The original mission parameters would be forgotten within the first fraction of a percent of the journey. No human institution has maintained coherent records for more than a few thousand years. The travelers would retain no accurate information about why they launched, where they came from, or what Earth was like. Their mythology might include garbled references to a homeworld, but these legends would bear as much resemblance to actual Earth as our own myths bear to the reality of prehistoric events they dimly recall. The descendants arriving at Andromeda would share no meaningful connection with the civilization that launched them. They would be aliens, creatures who happen to share distant ancestry with the humans who built the original ship. They might not even recognize themselves as being on a journey. The ship would simply be their universe, the only reality they had ever known. But even this analysis understates the problem. It assumes we could somehow accelerate spacecraft to significant fractions of light speed, which presents its own insurmountable barriers. The energy requirements for such acceleration exceed anything humanity could realistically produce, no matter how advanced our technology becomes. The mathematics of acceleration reveals the true scale of the energy problem. Einstein's famous equation, E equals mc squared, tells us that mass and energy are equivalent. This beautiful formula contains a terrible implication for interstellar travel. As an object accelerates toward light speed, its effective mass increases, requiring ever more energy to continue accelerating. The faster you go, the heavier you become, and the more energy you need to go faster still. The relationship is not linear, but exponential. The energy required to reach even 90% of light speed exceeds the total energy output of our Sun for years of continuous burning. Accelerating a modest spacecraft weighing about 1,000 kilograms, roughly the mass of a small car, to 90% of light speed would require approximately 7 times 10 to the 19th joules of energy. This equals the total energy output of the Sun for about 2 seconds. 2 seconds of solar output focused entirely on accelerating a single small vehicle. For a spacecraft capable of carrying humans and the life support systems they require, weighing perhaps 1 million kilograms, the energy requirement rises to about 7 times 10 to the 22nd joules, the entire annual energy consumption of human civilization. All the electricity generated by every power plant on Earth, all the fuel burned by every vehicle, all the energy used by every factory and home and server farm equals approximately 6 times 10 to the 20th joules. Accelerating a single human spacecraft to 90% of light speed would require more energy than humanity uses in over 100 years. Every joule of electricity generated by every nation on Earth for a century would need to be focused entirely on pushing one ship slightly closer to the cosmic speed limit. And this calculation completely ignores the energy needed to decelerate upon arrival, which would roughly double the total requirement. No propulsion system currently imagined could deliver such enormous quantities of energy to a spacecraft. Chemical rockets, the workhorses of current space travel, produce thrust by burning fuel and expelling the combustion products. They cannot even begin to approach the required velocities. A chemical rocket would need to carry fuel masses exceeding the mass of the Earth to achieve even a few % of light speed. Nuclear pulse propulsion, which would use nuclear explosions to accelerate spacecraft, represents one of the more extreme propulsion concepts ever seriously studied. Project Orion, during the 1950s and 60s, proposed a ship that would drop nuclear bombs behind itself and ride the resulting shockwaves. Such a vessel might achieve a few % of light speed after decades of continuous operation and thousands of nuclear detonations. But a few % of light speed only reduces the journey time from trillions of years to hundreds of millions of years. The improvement is dramatic, but meaningless for practical purposes. Antimatter engines, which would annihilate matter to produce pure energy according to Einstein's equation, remain purely theoretical. Antimatter provides the highest energy density possible in physics, converting 100% of mass into energy rather than the fraction of a percent achieved by nuclear reactions. But we currently produce antimatter at rates measured in nanograms per year, at costs measured in trillions of dollars per gram. Accelerating a single human spacecraft to Andromeda would require producing antimatter in quantities measured in thousands of tons. The gap between our current capabilities and the requirements for antimatter propulsion spans more than 20 orders of magnitude. The distance to Andromeda, combined with the energy requirements for approaching light speed, creates a barrier that no amount of engineering cleverness can overcome. We are not lacking in ambition or creativity or intelligence. We are not making simple mistakes that better scientists might correct. We are fighting against the fundamental structure of the universe itself, against mathematical relationships embedded in the deepest foundations of physical reality. The energy barrier does not represent a temporary technological limitation. It emerges from the same physics that allows stars to shine and atoms to exist. Circumventing it would require violating the most thoroughly tested equations in science, equations confirmed by millions of experiments over more than a century. The energy requirements for intergalactic travel are not engineering challenges to be solved, but physical laws to be obeyed. But the distance barrier, as insurmountable as it appears, represents only the first wall of our cosmic prison. The second wall is constructed from the very fabric of space-time itself, woven from threads of light and causality, and it is far more absolute than any mere measurement in miles or any calculation of energy requirements. The first barrier says we cannot get there quickly. The second barrier says we cannot get there at all. In 1905, a 26-year-old patent clerk working in Bern, Switzerland, published a paper that would forever change humanity's understanding of space, time, and motion. His name was Albert Einstein, and he spent his days examining patent applications for electromagnetic devices, while his nights consumed him with questions about the nature of light. That year, he published 4 papers that revolutionized physics. But one of them contained a single devastating conclusion that has imprisoned every civilization in the universe for the past 13.8 billion years. Nothing can travel faster than light. This statement sounds almost quaint when you first hear it. Of course, there must be some speed limit, you think. Perhaps it represents an engineering challenge, a barrier that sufficiently advanced technology might someday overcome. Perhaps it reflects the limitations of 1905 physics, constraints that modern science has since transcended. Perhaps some clever loophole exists, some trick of quantum mechanics or exotic geometry that could circumvent the cosmic speed limit. None of these hopes survive contact with the actual physics. The speed of light does not represent a mere engineering challenge to be overcome with better rockets or more powerful engines. It is not a barrier waiting for some genius to find a way around. like the sound barrier that pilots once thought unbreakable. The speed of light represents a fundamental property of space-time itself, woven into the deepest mathematical structure of reality, with threads that cannot be cut or untangled. Exceeding light speed is not just difficult or currently impossible. It is literally meaningless within the framework of physics as we understand it. To grasp why this barrier is absolute, you must understand what Einstein discovered about the relationship between space, time, and motion. Before relativity, scientists assumed that space and time were separate entities, each fixed and universal. Everyone experienced the same time regardless of how they moved. A clock on a speeding train kept the same time as a clock on the station platform. Space measured the same distances for all observers. A meter stick remained a meter long whether it sat motionless or hurtled through the cosmos at tremendous speed. These assumptions seem intuitively obvious. They match our everyday experience perfectly. When you walk across a room, you do not notice time flowing differently than it does for someone standing still. When you drive down a highway, your car does not shrink in the direction of travel. The world appears to behave exactly as Isaac Newton described it 3 centuries ago, with absolute space and absolute time providing the fixed stage upon which events unfold. Einstein proved these intuitive assumptions catastrophically wrong. Space and time are not separate. They are woven together into a single 4-dimensional fabric that physicists call space-time. They are aspects of the same underlying reality, united by mathematics that Einstein derived from first principles while working at that patent office in Bern. Motion through space affects your experience of time. This is not a metaphor or a philosophical statement. It is a precise mathematical relationship confirmed by countless experiments over more than a century. The faster you move through space, the slower you move through time relative to stationary observers. Approach the speed of light, and time itself begins to slow down. At light speed, if you could somehow reach it, time would stop completely. This phenomenon, called time dilation, is not a theory awaiting confirmation. Scientists have tested relativistic time dilation thousands of times, using particle accelerators that send subatomic particles racing at 99.999% of light speed. They have confirmed it using precise atomic clocks flown on aircraft and satellites. They have observed it in cosmic rays, in the decay rates of unstable particles, in the behavior of GPS satellites that must account for relativistic effects to maintain accuracy. Every experiment confirms Einstein's predictions with extraordinary precision. The mathematics of special relativity has been verified to more decimal places than almost any other theory in physics. Time dilation is real, measurable, and has profound implications for any attempt to travel between galaxies. Consider what happens as a spacecraft accelerates toward Andromeda. At low velocities, the velocities of cars and planes, and even our fastest rockets, relativistic effects remain negligible. Time aboard the spacecraft runs at essentially the same rate as time on Earth. The difference would be measured in billionths of a second over years of travel, detectable only with the most sensitive instruments. But as speed increases, as the spacecraft climbs towards significant fractions of light speed, time aboard begins running noticeably slower compared to time on Earth. The relationship follows a precise mathematical formula involving the square root of 1 minus velocity squared divided by the speed of light squared. At 50% of light speed, spacecraft time runs at about 87% of Earth time. For every year that passes aboard the ship, about 1.15 years pass on Earth. At 90% of light speed, approximately 600 million miles per hour, spacecraft time runs at about 44% of Earth time. For every year aboard the ship, more than 2 years pass on Earth. The travelers age more slowly than those they left behind. They watch Earth's calendar race ahead of their own. Centuries compressed into decades, millennia into centuries. At 99% of light speed, time aboard the spacecraft slows to about 14% of Earth time. For every year the travelers experience, More than 7 years pass in the universe outside their vessel. They become time travelers in the most literal sense, leaping into the future while their bodies age at a fraction of the normal rate. At 99.9% of light speed, spacecraft time drops to about 4% of Earth time. At 99.99%, it falls to about 1.4%. The closer you approach light speed, the more dramatically time slows aboard your vessel. The mathematics curves asymptotically towards zero as velocity approaches the cosmic speed limit. This time dilation creates a profound and disturbing asymmetry between travelers and those left behind. Imagine astronauts aboard a spacecraft traveling at 99% of light speed toward Andromeda. From their perspective, time passes normally. Their clocks tick at the usual rate. Their hearts beat with the usual rhythm. Their conversations unfold at the usual pace. They experience no subjective sense of time moving differently. But from their accelerated reference frame, the journey would still take approximately 350,000 years of subjective time, 350,000 years of living aboard a spacecraft, watching stars drift slowly past, waiting for the destination to grow nearer. Still inconceivably long, but perhaps imaginable for some form of advanced civilization with life extension, technology, or generation ships spanning thousands of generations. Meanwhile, on Earth, 2.5 million years would pass. The travelers would arrive at Andromeda to find that everyone they ever knew had died millions of years before. Their friends, their families, their entire civilization, their entire species, all would have vanished into the mists of prehistoric time. Human civilization would have either evolved beyond recognition, developing into something as incomprehensible to the travelers as we would be to Australopithecus, or it would have destroyed itself through war, environmental collapse, or some catastrophe we cannot imagine, or it would have simply vanished, gone extinct like 99% of all species that ever lived, leaving no descendants to greet the returning travelers. The astronauts would be refugees from a prehistoric era arriving in an inconceivable future. If they somehow turned around and made the return journey, another 2.5 million years would pass on Earth before they arrived home. They would return to a planet that had experienced 5 million years of history since their departure, inhabited by beings who might not recognize them as ancestors, who might not even remember that the human species ever existed. There would be no possibility of ever returning to the world they left behind. That world would be gone, erased by millions of years of change. Its continents drifted to new positions. Its species evolved or extinct. Its civilizations crumbled to dust that itself had crumbled to smaller dust billions of times over. But relativistic time dilation, as strange and disturbing as it seems, does not represent the fundamental barrier to intergalactic travel. It creates problems, certainly, problems that would render any journey to Andromeda meaningless for those who launched it. The true prison wall emerges from what happens as you try to accelerate toward light speed itself. As an object with mass accelerates, its effective mass increases according to relativistic equations. This is not some trick of measurement or perspective. The object genuinely behaves as if it has more mass, requiring more force to accelerate further, exhibiting greater gravitational effects, possessing more kinetic energy than classical physics would predict. At low speeds, this mass increase is negligible. A car traveling down a highway has effectively the same mass whether it moves at 50 miles per hour or 70. The difference would be unmeasurable with any instrument, hidden in the noise of experimental uncertainty. But as you approach light speed, the mass increase becomes dramatic. At 90% of light speed, an object has about 2.3 times its rest mass. A spacecraft that massed 1,000 tons at rest would behave as if it massed 2,300 tons at this velocity. At 99% of light speed, the same spacecraft would have about 7 times its rest mass, behaving as if it weighed 7,000 tons. At 99.9%, it would have about 22 times its rest mass. This mass increase requires correspondingly more energy to continue accelerating. The faster you go, the heavier you become. and the more energy you need to go faster still. Each increment of velocity requires more energy than the previous increment. Each step toward light speed becomes harder than the last. The mathematics creates an asymptotic barrier that no amount of energy can breach. As you approach light speed, the energy required to continue accelerating approaches infinity. Not a very large number. Not a number so big we cannot currently produce it. Infinity. The actual mathematical limit of the function as velocity approaches the speed of light is infinite energy. No finite amount of energy can accelerate any object with mass to exactly the speed of light. You can get arbitrarily close, spending ever-increasing quantities of energy for ever smaller velocity gains. You can reach 99% of light speed if you have enough energy. You can reach 99.9% if you have vastly more. You can reach 99.99% if you somehow command energy supplies exceeding the output of stars. But the final gap between your velocity and light speed remains unbridgeable regardless of how much energy you expend. That last fraction of a percent would require infinite energy to cross. And infinite is not a number you can generate with better reactors or more advanced technology. It is a mathematical concept representing a limit that cannot be reached through any finite process. This is not a technological limitation awaiting solution. The equations of special relativity do not permit massive objects to reach or exceed light speed. They do not contain loopholes or exceptions. They describe reality with a precision that has been verified millions of times by millions of experiments. The universe does not care about human ingenuity or alien technology or the desperate hope of civilizations yearning to spread among the stars. The laws of physics apply equally to every civilization that has ever existed or ever will exist. A species that has mastered fusion power faces the same cosmic speed limit as a species that has harnessed the energy of black holes. A civilization spanning a galaxy faces the same barrier as bacteria crawling across a petri dish. The mathematics does not make exceptions. Light travels at exactly 299,792,458 meters per second in a vacuum. This value is not arbitrary, not a cosmic accident, not something that might have been different in another universe with different fundamental constants. It is the speed at which massless particles traverse space-time, built into the geometry of the cosmos at the deepest level physics can probe. This speed represents the conversion factor between space and time, the ratio that relates the two aspects of space-time to each other. It appears in countless physical equations governing everything from electromagnetism to nuclear physics to the structure of atoms. Changing the speed of light would not simply allow faster travel, it would unravel the laws of physics that make matter possible. Anything massless like light itself must travel at exactly this speed, never faster, never slower. Some popular science discussions suggest that humanity might someday discover how to travel faster than light through wormholes, warp drives, or other exotic phenomena. These concepts populate science fiction with thrilling possibilities. Starships jump through hyperspace, crews surf on folded space-time, civilizations span galaxies in vessels that somehow slip the bonds of relativistic physics. While these concepts make for entertaining stories, they face extraordinary obstacles in actual physics that the fiction typically ignores or waves away with technobabble. Wormholes, theoretical tunnels through space-time that would connect distant regions, remain purely mathematical constructs with no observational evidence for their existence. The equations of general relativity permit their existence under certain conditions, but those conditions require exotic matter with negative energy density to keep the wormhole throat open and traversable. No such matter has ever been observed in nature. Theoretical analyses suggest that exotic matter with the required properties may violate fundamental principles like the second law of thermodynamics, which governs the direction of time and the increase of entropy. If exotic matter violates thermodynamics, then it cannot exist in any stable form, and wormholes cannot be constructed or traversed. Even if stable wormholes could somehow be created through physics we do not yet understand, traveling through them might violate causality itself, creating paradoxes that suggest such travel is impossible in principle. A traversable wormhole could potentially be transformed into a time machine, allowing travelers to arrive before they departed. The logical contradictions this would create, the so-called grandfather paradox and its variants, suggest that the universe contains some mechanism preventing such closed time-like curves from forming. The Alcubierre warp drive, proposed in 1994 by physicist Miguel Alcubierre, describes a theoretical method for apparent faster-than-light travel by manipulating spacetime itself. The concept involves contracting space in front of a spacecraft while expanding it behind, creating a bubble of flat spacetime that carries the vessel along at effectively superluminal velocities. This sounds promising until you examine the requirements. The Alcubierre metric requires exotic matter with negative energy density in quantities exceeding the mass energy of the entire observable universe in some formulations. Even optimized versions of the concept require energy equivalent to converting Jupiter, the largest planet in our solar system, into pure radiation. This exceeds human energy production by factors so large they cannot be meaningfully expressed. More recent analyses suggest the Alcubierre warp bubble might be fundamentally unstable, collapsing catastrophically if disturbed. It might also destroy everything at the destination through a lethal burst of accumulated radiation released when the bubble slows down. Scientists have also proposed that quantum entanglement might allow faster-than-light communication, circumventing the light barrier, at least for information transfer, even if physical travel remains impossible. Quantum entanglement creates correlations between particles that persist regardless of distance. Measure one particle and the other instantly reflects the result, no matter how far apart they are. This instantaneous correlation sounds like it should allow faster-than-light signaling. If you could manipulate your particle and have the distant particle respond immediately, you could transmit information across any distance without delay. But careful analysis reveals that quantum entanglement cannot transmit information faster than light. The correlations are real, but they are statistical in nature. You cannot choose what result your measurement will produce. You can only observe the random outcome. The distant particle responds to your measurement, but the response is random. Only when you later compare results through a conventional light-speed channel does the correlation become apparent. This limitation is not a technological obstacle. It is built into the mathematics of quantum mechanics itself. The no-communication theorem proves rigorously that quantum entanglement cannot be used to send messages faster than light. The proof rests on fundamental properties of quantum mechanics that have been verified experimentally thousands of times. The light barrier represents physics in its most absolute form. Every proposed method for circumventing it either requires impossible quantities of energy, violates fundamental principles of physics, or turns out to be theoretically inconsistent upon detailed mathematical analysis. The barrier stands because the mathematics of spacetime does not permit massive objects to travel at or above light speed. This is not a statement about current technology or human understanding. It is a statement about the structure of reality. But the cosmic speed limit creates consequences even more disturbing than simply preventing rapid travel. It shapes the structure of causality itself and determines what events can influence other events throughout the universe. Consider two events occurring in different locations. Event A happens on Earth. Perhaps it is you reading these words at this very moment. Event B happens in Andromeda, 2.5 million light-years away. Perhaps it is an alien civilization launching a spacecraft from one of Andromeda's trillion stars. Special relativity reveals that these events can have one of three possible relationships, determined entirely by the geometry of spacetime. If Event A could have caused Event B through some signal traveling at or below light speed, they have a causal relationship. Event A is in the causal past of Event B. A light beam sent from Earth at Event A could arrive at Andromeda in time to influence Event B. Information from our location could reach their location before their event occurred. If Event B could have caused Event A through such a signal, Event B is in the causal past of Event A. Their action could have influenced ours, but if the events are too far apart in space and too close together in time for any light-speed signal to connect them, they have no possible causal relationship. No signal from either event could reach the other before both have already occurred. They exist in what physicists call a space-like separation, meaning the spatial distance between them exceeds the distance light could travel in the time between them. For events separated by space-like intervals, relativity reveals something deeply strange that defies human intuition. Different observers moving at different velocities will disagree about which event happened first. For some observers, Event A precedes Event B. For others, Event B precedes Event A. And here is the disturbing part. Both perspectives are equally valid. Neither observer is wrong. The concept of which happened first has no absolute answer. This is not a mere philosophical curiosity or a trick of measurement. It reveals that simultaneity, the concept of two events happening at the same time, has no absolute meaning for events separated by space-like intervals. Two observers in relative motion will genuinely disagree about the order of distant events, and physics provides no way to determine which observer is correct because the question itself has no objective answer. The entire concept of now breaks down across intergalactic distances. When you look at Andromeda tonight, you see light that left 2.5 million years ago. You observe the galaxy as it existed when your ancestors were learning to walk upright. But what is happening in Andromeda right now, at this very moment, simultaneously with your reading of these words? The question has no definitive answer. For an observer moving rapidly toward Andromeda, their now in Andromeda might include events that from Earth's perspective happened millions of years in the past. For an observer moving rapidly away from Andromeda, there now might include events that from Earth's perspective will not happen for millions of years in the future. Both observers are correct. Both are measuring time accurately with properly functioning clocks. They simply disagree about what distant now means, and the mathematics of relativity provides no way to choose between them because there is no fact of the matter to discover. The light barrier does not merely prevent rapid travel. It fragments the universe into regions that can never share a common present. Each location exists in its own isolated bubble of now, connected to other locations only through light signals that require vast time spans to traverse the intervening distance. The present moment you experience on Earth has no counterpart in Andromeda. The concept of the present moment in Andromeda is undefined, depending on your motion in ways that physics cannot resolve. This fragmentation has profound implications for any hypothetical galactic or intergalactic civilization. Science fiction commonly imagines empires spanning multiple star systems, coordinated by some form of government or organization that manages affairs across light years of distance. Fleets respond to orders from a central command. Colonies send taxes and tribute to an imperial capital. News travels across the galaxy, keeping citizens informed about distant events. The light barrier proves such coordination impossible. Even within our own galaxy, signals take 100,000 years to cross from one edge to the other. An order sent from the galactic center to the rim would arrive 100,000 years after it was issued. Any response would take another 100,000 years to return. A simple exchange of messages would span 200,000 years. No empire could function across such timescales. No government could respond to crises. No military could coordinate campaigns. By the time news of a rebellion reached the capital and orders to suppress it returned, 200,000 years would have passed. The rebellion would have succeeded or failed, evolved into a new civilization, risen to glory and declined to dust, all before the response to its initial outbreak arrived. Any galactic civilization would necessarily consist of essentially independent regions, each evolving according to its own timeline, unable to coordinate with distant territories except through messages requiring millennia for exchange. The light barrier creates not merely physical isolation but causal isolation, dividing the cosmos into regions that can observe each other but never interact in any meaningful time frame. The light barrier creates something physicists call the cosmic horizon, a sphere surrounding every observer beyond which no signals can ever arrive within the finite age of the universe. Events outside your cosmic horizon can never influence you because no information from those regions can reach your location before the universe ends. For Andromeda, the light travel time of 2.5 million years means that anything happening there right now cannot affect Earth for another 2.5 million years. We exist in complete causal isolation from current events in our nearest major galactic neighbor. Whatever is happening there now, whatever civilizations are rising or falling, whatever stars are being born or dying, will not influence our planet until human civilization has existed for more than 8 times longer than it currently has. The speed of light does not merely limit how fast we can travel. It determines what parts of the universe can ever interact with us, what events can ever influence our future, and what information we can ever receive about cosmic neighbors. The light barrier is not a wall to be climbed or a river to be crossed. It is the fundamental architecture of space-time, defining the boundaries of causality itself, determining what can cause what throughout the entire cosmos. We are not trapped behind a barrier that separates us from Andromeda. We are embedded in a space-time geometry that makes the very concept of now in Andromeda meaningless. We cannot travel there quickly because the mathematics of mass and energy forbids it. We cannot communicate there quickly because no signal can exceed the speed of light. We cannot even say what is happening there right now because the concept of right now has no objective meaning across such distances. But even the light barrier does not represent the final wall of our cosmic prison. A third barrier exists, one that makes the first two seem almost trivial by comparison. This barrier is not a law of physics that might someday be circumvented by civilizations smarter than us. It is not a mathematical limit that applies only to current understanding. It is the fabric of reality itself, expanding between us and Andromeda with every passing moment, stretching the void wider even as you read these words. In 1929, astronomer Edwin Hubble sat in the observer's cage of the 100-inch Hooker telescope at Mount Wilson Observatory, perched high above the lights of Los Angeles. Night after night, he photographed distant galaxies, measuring their light with painstaking precision. He was searching for a pattern in the cosmos, some organizing principle that might reveal how the universe was structured. What he discovered would permanently alter humanity's understanding of cosmic geography and seal our fate as prisoners of an expanding void. By measuring the light from distant galaxies, Hubble found something unexpected and deeply disturbing. Almost every galaxy in the universe is moving away from us. Not just a few galaxies, not just galaxies in one particular direction. Nearly all of them, in every direction he looked, were receding from Earth as if fleeing some cosmic catastrophe centered on our location. Even more strange, the more distant the galaxy, the faster it appeared to recede. A galaxy 10 million light-years away was moving away at a certain speed. A galaxy 20 million light-years away was moving away twice as fast. A galaxy 100 million light-years away was receding 10 times faster still. The relationship was precise and linear, now known as Hubble's law. This pattern seemed to suggest that Earth occupied some special central position, with all other galaxies rushing away from us like debris from an explosion. But Hubble and his colleagues realized the truth was stranger and more profound. Space itself is stretching, carrying galaxies apart like dots painted on an inflating balloon. Imagine those dots on a balloon's surface. As you blow air into the balloon, the rubber stretches and the dots move apart. No dot is at the center of the expansion. Every dot sees all other dots receding from it. The dots closer together separate more slowly. The dots farther apart separate more quickly. This is not because the dots are moving across the rubber surface. It is because the rubber itself is growing, increasing the distance between all points simultaneously. Hubble had discovered that the universe is expanding. The fabric of space-time grows with every passing moment, stretching the distances between cosmic structures that are not held together by gravity. This expansion operates at every scale larger than gravitationally bound systems like galaxy clusters. Individual galaxies hold themselves together through gravity. Galaxy clusters maintain their coherence through mutual attraction, but the space between these structures expands relentlessly, carrying them apart across the cosmic void. This discovery revealed something terrifying about the distance to Andromeda. That already impossibly vast gulf of 2.5 million light-years is not a fixed quantity. It changes over time as cosmic expansion stretches the space between galaxies. The universe you wake up to tomorrow will be slightly larger than the universe you fell asleep in tonight. The distances between galaxies will have grown by imperceptible amounts during your rest, accumulating over cosmic time into expansions that dwarf human comprehension. For most of the universe's history, this expansion meant that reaching distant galaxies was becoming progressively more difficult with every passing second. The targets were retreating even as you contemplated the journey. The finish line was moving away faster than you could run toward it. The prison walls were growing higher and thicker with each tick of the cosmic clock. But Andromeda presents a peculiar exception that makes our situation even more complex and ultimately more tragic than simple expansion would suggest. Andromeda is approaching us. While cosmic expansion pushes most galaxies away from Earth, Andromeda and the Milky Way are gravitationally bound together within what astronomers call the local group. This gravitational attraction overwhelms cosmic expansion at our relatively close range of 2.5 million light-years. The two galaxies have been falling toward each other since shortly after they formed, their mutual gravity pulling them together across the intergalactic void. Andromeda approaches at approximately 250,000 miles per hour, closing the gap between our galaxies at a rate that would seem impressive by any earthly standard. At this velocity, you could travel from New York to Los Angeles in about 36 seconds. You could circumnavigate the globe in under 6 minutes. You could reach the moon in less than an hour. Yet this seemingly tremendous speed barely registers against intergalactic distances. At 250,000 miles per hour, Andromeda closes the gap by about 2.5 billion miles per year. This sounds like progress until you remember that the total distance measures approximately 15 million trillion miles. The approach velocity represents roughly 1/6 millionth of the total distance per year. In about 4.5 billion years, the two galaxies will finally collide and merge, their spiral arms intertwining in a gravitational dance lasting hundreds of millions of years. Computer simulations show the collision in exquisite detail. The galaxies will pass through each other, swing apart, fall back together, and eventually merge into a single, massive, elliptical galaxy that astronomers have already named Andromeda. This fact might seem to offer hope. If Andromeda is getting closer, perhaps reaching it becomes progressively easier over cosmic timescales. Perhaps patience, rather than speed, represents the key to intergalactic travel. Perhaps we simply need to wait for our destination to come to us. But this hope proves illusory for multiple reasons, and the true implications of cosmic expansion reveal a far darker picture of our cosmic imprisonment than mere distance ever could. First, even though Andromeda approaches, the timescale of that approach exceeds any meaningful human horizon. 4.5 billion years will pass before the galaxies merge. During this time, our Sun will exhaust its hydrogen fuel and begin burning helium in its core. The Sun's outer layers will expand outward as it transforms into a red giant, likely engulfing Mercury and Venus, and almost certainly rendering Earth uninhabitable even if our planet escapes direct consumption. The oceans will boil away. The atmosphere will be stripped into space. By the time Andromeda arrives, our planet will have been dead for hundreds of millions of years, a scorched rock orbiting a swollen red star that itself will eventually collapse into a white dwarf. The approaching collision offers no practical benefit for any journey we might attempt. Andromeda draws nearer, but the timescale of that approach exceeds the lifespan of our planet, our Sun, and quite possibly our entire solar system. We cannot wait for our destination to arrive because we will not survive long enough to greet it. Second, and far more disturbing, Andromeda represents a rare exception within a universe that is largely receding from us at ever-increasing speeds. Our gravitational bond with Andromeda is a local anomaly, a temporary reprieve from cosmic expansion that applies only to our immediate galactic neighborhood. The real horror of cosmic expansion lies not in what it means for Andromeda, but in what it means for everything else in the observable universe. In 1998, two independent teams of astronomers made a discovery that shocked the scientific community and earned the Nobel Prize in Physics. They were studying distant supernovae, using these cosmic explosions as standard candles to measure the expansion rate of the universe at different epochs. They expected to find that cosmic expansion was slowing down over time, gradually decelerating as gravity pulled the universe's contents back together. Instead, they found the opposite. Cosmic expansion is not slowing down, it is accelerating. The universe is flying apart faster today than it was yesterday, and it will fly apart faster tomorrow than it does today. Some unknown force, which scientists have named dark energy for lack of any better understanding, is pushing the universe apart with increasing intensity. Dark energy comprises approximately 68% of the total energy content of the universe. It outweighs all the matter, both visible and dark, by a factor of more than 2 to 1. Yet we have no idea what it actually is. We can measure its effects with exquisite precision. We can model its influence on cosmic expansion. We can predict how it will shape the universe's future, but we cannot explain why it exists or what underlying physics gives rise to it. This ignorance haunts physicists. Dark energy is not merely unknown in the way that distant galaxies were once unknown, waiting for better telescopes to reveal them. It is unknown in a deeper, more troubling sense. The equations that describe its effects work perfectly. The predictions match observations with extraordinary precision, but the equations tell us nothing about what dark energy actually is or why it exists at all. The leading theoretical explanation, that dark energy represents the intrinsic energy of empty space itself, creates one of the most embarrassing failures in the history of physics. When scientists calculate how much energy empty space should contain based on quantum mechanics, they get a number that exceeds the observed value by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. No other prediction in science has ever been so catastrophically wrong. This discrepancy, known as the cosmological constant problem, suggests that our understanding of fundamental physics contains some enormous gap, some missing principle that would explain why the vacuum energy is so precisely fine-tuned to an almost but not quite zero value. Without this unknown principle, the universe should either have collapsed immediately after the Big Bang or expanded so rapidly that no structures could ever form. We exist in a cosmos balanced on a knife edge, and we have no idea why. Some theoretical models suggest that dark energy might not remain constant over cosmic time. It might strengthen, leading to a scenario called the Big Rip, where accelerating expansion eventually tears apart galaxies, then solar systems, then planets, then atoms themselves, ending the universe in a final catastrophic expansion approximately 22 billion years from now. Or dark energy might weaken, potentially reversing cosmic expansion and leading to a big crunch where the universe collapses back to a singularity. We cannot distinguish between these possibilities with current observations. The force that dominates our universe, that determines its ultimate fate, that will eventually isolate every civilization from every other, remains almost entirely mysterious. We know what dark energy does. We have no idea what it is. This accelerating expansion has consequences that dwarf any other barrier to intergalactic travel we have discussed. The distance barrier seemed insurmountable. The light speed limit appeared absolute, but cosmic expansion creates a prison wall that makes both of those seem almost minor by comparison. Beyond a certain distance from Earth, space expands faster than light itself can travel through it. Galaxies beyond this cosmic horizon are receding from us at effective velocities exceeding the speed of light. Wait, does that not contradict everything established earlier about the cosmic speed limit? Did we not just spend an entire section explaining that nothing can travel faster than light? Here lies one of the most counterintuitive aspects of modern cosmology, a subtlety that even many science enthusiasts misunderstand. Nothing can travel through space faster than light. This remains absolutely true. The cosmic speed limit applies to all objects moving through space-time, from particles to people to spacecraft to signals. But space itself faces no such limitation. The fabric of space-time can stretch at any rate whatsoever, carrying objects along with it at any effective velocity. There is no universal speed limit on the expansion of space, because expansion is not motion through space. It is the growth of space itself. Distant galaxies are not moving through space faster than light. They are essentially stationary in their local space-time, just as we are essentially stationary in ours. The Milky Way is not racing through the cosmos at some tremendous velocity. We are sitting still, floating in our local region of space, watching the universe expand around us. But the space between us and distant galaxies is expanding so rapidly that the effective separation velocity exceeds light speed. The galaxies themselves are not moving. The distance between us is growing because space is stretching. Think of it like two ants walking toward each other on a rubber sheet. If someone is stretching the rubber faster than the ants can walk, the ants will never meet despite their continuous forward progress. They are not moving backward. They are walking forward at their maximum speed, but the sheet is expanding faster than their walking pace, increasing the distance between them faster than they can close it. The ants might walk forever and never reach each other. They might exhaust themselves crawling across the rubber surface, making genuine forward progress measured against the local sheet, yet finding the total distance to their destination growing with each step, rather than shrinking. This is the situation facing any civilization attempting to travel beyond the cosmic horizon. For galaxies beyond approximately 14 billion light-years, currently the edge of what astronomers call the Hubble sphere, no signal we send can ever reach them. No matter how fast our signal travels, up to and including the speed of light, cosmic expansion will stretch the intervening space faster than the signal can cross it. These galaxies have passed beyond the possibility of any interaction with Earth. They are forever isolated from our cosmic neighborhood, receding into infinite separation as dark energy accelerates their departure. No message we transmit will ever arrive. No spacecraft we launch will ever reach them. No future technology, no matter how advanced, can bridge a gap that grows faster than light can cross. This cosmic horizon is not static. Dark energy causes accelerating expansion, which means the horizon is actually shrinking over time as measured from our perspective. Galaxies that we can currently observe are crossing beyond the horizon with each passing moment, disappearing from the potentially accessible universe forever. The expansion rate of space increases with distance. Nearby space expands slowly. Distant space expands quickly. As you look farther out, you eventually reach a distance where expansion velocity equals light speed. Beyond that distance, nothing can ever reach us, and we can never reach them. But accelerating expansion means that the distance at which this occurs is getting closer to us. Galaxies that currently lie just inside the horizon will soon cross outside it. The cosmic neighborhood we can theoretically access is shrinking, while the total universe continues growing. We are increasingly isolated within an ever smaller bubble of potentially reachable space. The observable universe extends far beyond the Hubble sphere, which creates a haunting asymmetry in our cosmic situation. We can see light from galaxies more than 40 billion light-years away. even though the Hubble sphere measures only about 14 billion light-years in radius. How is this possible? The light we see from those distant galaxies began its journey billions of years ago, when those galaxies were much closer to us. Space was smaller then, distances were shorter. The universe had not yet expanded to its current size. Photons that left those galaxies when the universe was young have been traveling through space that has been expanding around them ever since. During their journey, cosmic expansion carried the source galaxies beyond the Hubble sphere. Those galaxies now recede from us faster than light, but the photons themselves, already in flight, continued propagating through expanding space at their constant velocity of 186,000 miles per second. The photons are not affected by the recession velocity of their source. They simply travel through whatever space they find themselves in. Eventually, those ancient photons reached Earth, carrying images of galaxies that now lie forever beyond our reach. We observe their light as a record of their distant past, frozen moments from billions of years ago when they still occupied our cosmic neighborhood. But the galaxies themselves, as they exist now, occupy regions of space that no signal from Earth can ever reach. This means we can observe galaxies that we can never visit, communicate with, or influence in any way. We see their ancient light, their historical record, preserved in photons that have traveled through expanding space for billions of years. But they exist now in regions forever beyond our causal reach. We can look, but we can never touch. The observable universe is far larger than the accessible universe. We can see approximately 2 trillion galaxies scattered across the observable cosmos. But the vast majority of these galaxies already lie beyond the Hubble sphere. They are receding from us faster than light. No journey we could ever undertake would reach them. The cosmic horizon taunts us with images of neighbors we can never contact. Those 2 trillion galaxies, containing perhaps 100 billion trillion stars and countless planets, represent cosmic neighbors whose ancient light reaches us, even as their present reality recedes into eternal isolation. We observe them as they were billions of years ago. We will never know what they have become. But here is where the true tragedy of our situation becomes fully apparent. The accelerating expansion will eventually overcome even our gravitational bond with Andromeda and the other members of our local group. Current models predict that in approximately 2 trillion years, every galaxy beyond our local group will have crossed the cosmic horizon. The expansion of space will have carried them beyond the edge of accessibility, beyond the reach of any signal traveling at light speed, beyond any possible interaction with our cosmic neighborhood. Future astronomers living in the merged Andromeda galaxy will look out at the night sky and see only emptiness. No distant galaxies will shine in their telescopes. No cosmic structures will reveal themselves at any wavelength. The universe beyond their local gravitational oasis will appear completely, utterly, infinitely black. They will have no evidence that other galaxies ever existed. The cosmic microwave background radiation, that faint afterglow of the Big Bang that currently fills all of space with ancient light, will have been stretched by cosmic expansion to wavelengths too long to detect with any conceivable instrument. The evidence for the Big Bang itself will have disappeared. The expansion history of the universe will be erased from observational records. Future scientists might develop sophisticated theories about the origin and evolution of their cosmos, but they will have no way to test those theories against observations. The evidence will have vanished beyond the cosmic horizon, carried away by the relentless expansion of space. These future astronomers might never discover that the universe began in a hot, dense state. They might never know that their lonely galaxy once had trillions of neighbors. They might never understand that the cosmic microwave background once filled space with detectable radiation. They might never piece together the true history of a cosmos that has hidden its past behind walls of expanding emptiness. This ultimate isolation represents the true horror of cosmic expansion. We live during a brief window of cosmic history, a golden age of observational cosmology, when we can see billions of galaxies and detect evidence of the Big Bang. This window is closing. Dark energy is gradually drawing a curtain across the universe, hiding most of existence from any possible observation. We are privileged to live during an era when cosmic history remains legible, when the evidence of our universe's origin still lies within observational reach. Our descendants will not share this privilege. They will inherit a cosmos that has erased its own story, a universe that has hidden its past behind horizons of eternal expansion. Andromeda represents our last major opportunity for intergalactic interaction, our final chance to reach beyond our galaxy before the cosmic curtain falls. Once the Milky Way and Andromeda merge 4.5 billion years from now, no other large galaxy will remain accessible. We will be imprisoned within our local group forever, surrounded by cosmic expansion that carries everything else beyond reach. The physics of cosmic expansion reveal something profound and disturbing about the structure of the universe we inhabit. Most of the galaxies we can currently observe are already moving away from us faster than we could ever travel. Even at the speed of light, we could not reach them. Even with propulsion systems beyond our wildest imagination, we could not catch destinations that recede faster than any possible approach velocity. The expansion of space creates an effective barrier that makes the light speed limit seem almost generous by comparison. Light speed restricts how fast we can travel through space. Cosmic expansion restricts how much space we can access at all. The first barrier slows our journey. The second barrier eliminates the destination entirely. Consider the implications for any civilization attempting intergalactic travel. Even if some advanced species discovered how to travel at 99% of light speed, they could only reach galaxies within a limited cosmic neighborhood. Beyond a certain distance, space expands too rapidly for any sublight journey to succeed. The travelers would never arrive because their destination would continuously recede faster than they could approach. This creates what physicists call the Hubble volume or Hubble sphere, the region of space where recession velocities remain below light speed. Only destinations within the Hubble sphere can be reached through normal spacetime travel. The Hubble sphere currently measures approximately 14 billion light-years in radius. This sounds enormous, and it contains billions of galaxies that theoretically remain accessible. But dark energy acceleration is shrinking this radius over cosmic time. We are not expanding into a larger accessible universe. We are contracting into a smaller one. They are closing in, slowly but inexorably, as dark energy accelerates cosmic expansion beyond the ability of even light-speed travelers to overcome. Cosmic expansion transforms the universe from a connected cosmos into an archipelago of increasingly isolated islands. Each gravitationally bound structure, each galaxy cluster, represents an island in an expanding ocean. The islands themselves are not moving apart. They are held together by gravity, maintaining their coherence against the expanding void. But the ocean between them is growing without limit, stretching the distances between islands until no voyage could ever bridge the gap. For humanity, imprisoned on one planet, in one solar system, in one galaxy, the expanding universe represents the ultimate prison wall. Even if we somehow escaped Earth, colonized the Milky Way, and developed technology beyond our current imagination, cosmic expansion would still confine us to a finite cosmic volume. Most of the universe would remain forever beyond reach, expanding away into permanent isolation. Andromeda, visible tonight as a faint smudge of light in the autumn sky, represents the boundary of human aspiration. Beyond our local group lies a universe that is already receding toward infinity, carrying most of cosmic existence beyond any possible interaction with our civilization. We can see it. We can study it. We can marvel at its vastness and complexity, but we can never touch it. Everything we have discussed so far concerns physics and cosmology, distance measured in millions of light-years, speed limits woven into the fabric of space-time, expanding space that carries galaxies beyond any possible reach. These barriers would challenge any civilization in the universe, regardless of intelligence, technology, or the billions of years they might have to develop solutions. They are universal constraints, cosmic laws that apply equally to bacteria and superintelligences, to species that emerged yesterday, and species that have existed since the first stars ignited. But for humanity specifically, for these fragile arrangements of carbon and water that call themselves conscious beings, additional constraints make reaching Andromeda not merely impossible but essentially unimaginable. The cosmic barriers would stop any civilization. The human barriers would stop us, even if the cosmic ones somehow disappeared. Consider the energy requirements for any realistic attempt at intergalactic travel. Not theoretical energy, not energy that might someday be harnessed by sufficiently advanced technology. Actual energy that would need to be produced, stored, and converted into propulsive force by systems that obey the laws of thermodynamics. The most energetic propulsion system ever seriously proposed by mainstream physics is the nuclear pulse drive, a concept that sounds like science fiction, but was actually studied extensively by the United States government during the 1950s and 60s. Project Orion, as the study was called, proposed a spacecraft that would detonate nuclear bombs behind itself and ride the resulting shockwaves through space. Each explosion would push against a massive plate at the rear of the ship, accelerating the vessel in a series of violent jolts. The concept works on paper. The physics checks out. Nuclear explosions release enormous quantities of energy that could theoretically be directed to provide thrust. A sufficiently large Orion spacecraft, detonating sufficiently powerful nuclear devices at a sufficiently rapid rate for sufficiently long, might achieve velocities of 3 to 5% of light speed, perhaps even higher. With optimistic assumptions about engineering capabilities, at 3% of light speed, approximately 20 million miles per hour, reaching Andromeda would require approximately 83 million years of travel time. 83 million years. This exceeds the entire existence of complex multicellular life in Earth's oceans. Dinosaurs went extinct only 66 million years ago, after dominating the planet for over 170 million years. The journey to Andromeda at nuclear pulse velocities would last longer than the combined lifespans of every dinosaur species that ever existed. Longer than the entire Mesozoic era, longer than most geological periods in Earth's history. But even achieving 3% of light speed presents prohibitive challenges that dwarf any engineering project humanity has ever contemplated. The fuel requirements for such a journey would exceed any quantity our civilization could realistically produce. Not just with current technology, but with any foreseeable expansion of industrial capability. You would need not just nuclear bombs, but millions of them. Each bomb would require enriched uranium or plutonium, materials that take years to produce in specialized facilities consuming enormous quantities of energy. The global stockpile of nuclear weapons, accumulated over decades of Cold War production at costs measured in trillions of dollars, contains perhaps 15,000 warheads. An Orion spacecraft traveling to Andromeda might require millions of such devices, perhaps tens of millions, depending on the desired velocity and payload mass. Manufacturing this much nuclear material would consume resources exceeding the current global economy for centuries. Every uranium mine on Earth would need to operate at maximum capacity. Every enrichment facility would need to run continuously. Every plutonium production reactor would need to breed fissile material around the clock. And all of this industrial output, sustained for generations, would produce fuel for a single spacecraft that would still require 83 million years to reach its destination. The fuel mass problem creates what rocket scientists call the tyranny of the rocket equation, a mathematical relationship that has constrained space travel since the first rockets lifted off from Earth and will continue constraining it until the laws of physics themselves change. To accelerate a payload to high velocities, you need fuel. This seems obvious enough. Rockets carry propellant that they burn and expel to generate thrust. The more thrust you need, the more fuel you must carry. But here lies the tyranny. That fuel itself has mass that must be accelerated, along with the payload. So, you need more fuel to accelerate the fuel, which requires more fuel to accelerate that additional fuel, which requires still more fuel to accelerate that additional fuel. The mathematics creates an exponential relationship that becomes prohibitive for high-velocity missions. For every increment of velocity you wish to add, you must multiply your fuel mass by a certain factor. These factors compound multiplicatively rather than additively. Doubling your desired velocity does not double your fuel requirement. It might increase it by a factor of 10 or 100 or 1,000, depending on the efficiency of your propulsion system. For a nuclear pulse drive capable of reaching 3% of light speed, the fuel mass would exceed the payload mass by ratios of hundreds or thousands to 1. A spacecraft carrying 1,000 people to Andromeda, along with the life support systems, radiation shielding, food production facilities, and redundant equipment necessary for an 83 million year journey, might mass several million tons before adding any fuel. The fuel required to accelerate this mass to 3% of light speed would itself mass billions of tons, and you would need additional fuel to decelerate upon arrival, roughly doubling the total requirement. The final spacecraft, fully fueled and ready to launch, would mass more than some asteroids. Building it would require mining and processing quantities of material, exceeding all human industrial output throughout history. And this represents the most optimistic propulsion technology within the realm of physics as we currently understand it. Nuclear pulse propulsion actually works. The physics is sound. The engineering, while challenging, does not violate any known laws. This is what the best-case scenario looks like, and it already exceeds human capabilities by factors that render the concept meaningless. More exotic propulsion concepts like antimatter engines or fusion drives face even more severe constraints, not less. Antimatter provides the most efficient energy conversion possible within known physics, converting 100% of mass into energy, according to Einstein's famous equation. When matter meets antimatter, both annihilate completely, releasing energy without the inefficiencies that plague chemical or nuclear reactions. A single gram of antimatter, annihilating with a gram of normal matter, would release energy equivalent to the Hiroshima bomb. A kilogram would release energy equivalent to a large thermonuclear weapon. The energy density of antimatter exceeds chemical fuels by factors of billions. It represents the ultimate propellant, the theoretical maximum of what physics permits for converting mass into thrust. But we currently produce antimatter at rates measured in nanograms per year. The entire global output of antimatter, accumulated across decades of particle physics research at facilities costing billions of dollars to construct and operate, amounts to less than a microgram. A single gram of antimatter, produced at current rates, would require billions of years of continuous production and would cost more than the entire economic output of human civilization throughout history. A single gram. An antimatter rocket capable of reaching Andromeda within 1 million years, let alone within any human-relevant time frame, would require antimatter measured not in grams but in megatons. Millions of tons of the most expensive substance ever produced by human technology. This exceeds our current production capacity by factors of 10 to the 27th power, or more. That is a 1 followed by 27 zeros. No conceivable expansion of antimatter production could bridge this gap within any relevant time frame. The numbers are not merely large, they are physically meaningless. The energy budget for intergalactic travel reveals a fundamental mismatch between human capabilities and cosmic requirements. We are attempting to cross distances that require energy budgets exceeding our entire civilization's output for millions of years. The total energy consumption of human civilization since the Industrial Revolution, all the coal burned, all the oil extracted, all the nuclear power generated, all the renewable energy harvested, amounts to a trivial fraction of what intergalactic travel would require. The gap between what we can produce and what intergalactic travel requires is not a percentage or a multiplier. It is more than 20 orders of magnitude. 20 orders of magnitude means a factor of 100 billion. It means that even if human energy production increased by a factor of 1,000,000, we would still fall short by a factor of 100 trillion. The gap is not a challenge to be overcome. It is an abyss that separates human capability from cosmic requirement. But energy represents only one dimension of the problem. Perhaps not even the most fundamental dimension. Human biology creates constraints that no amount of energy could fully address. Limitations written into our cells and organs and chromosomes by 4 billion years of evolution on a single world. Human bodies evolved for conditions on Earth. Our cells function within narrow parameters of temperature, requiring liquid water to operate their chemical machinery. Our organs expect specific gravitational forces, specific atmospheric pressures, specific radiation environments. Our immune systems evolved to fight pathogens found on Earth, not the novel microorganisms that might evolve aboard spacecraft over millions of years. Our bones expect regular stress from gravity to maintain their density. Our muscles expect regular use against resistance to maintain their strength. Our cardiovascular systems expect specific pressure gradients that change when gravity changes. Space travel subjects human bodies to conditions far outside these parameters, causing documented health effects that accumulate over time. Astronauts returning from 6-month stays aboard the International Space Station show measurable bone density loss, sometimes exceeding 1% per month. Their muscles atrophy despite exercise regimens designed to counteract weightlessness. Their cardiovascular systems adapt to microgravity in ways that cause problems upon return to Earth. Their immune systems weaken. Their cancer risk increases from radiation exposure. Current technology can sustain human life in space for periods of months to perhaps a few years with significant health consequences. The International Space Station maintains crews for typically 6-month rotations, carefully managed durations designed to limit the physiological damage of extended spaceflight. Longer stays cause measurable changes that require months of recovery after return to Earth. A journey to Andromeda lasting millions of years would require biological solutions far beyond current understanding or any foreseeable medical technology. Either human bodies would need to be fundamentally re-engineered to withstand indefinite space travel, transformed at the genetic level into something capable of surviving conditions our ancestors never experienced, or some form of suspended animation would need to preserve human biology across timescales exceeding the existence of our species. Neither option appears achievable with any technology grounded in current scientific understanding. Suspended animation, the science fiction trope of freezing travelers for long journeys, remains pure fiction with no clear pathway to implementation. Current cryopreservation techniques cannot preserve complex organisms. Ice crystals form during freezing, rupturing cell membranes and destroying tissue structure. Antifreeze compounds can reduce this damage, but cannot eliminate it. No mammal has ever been frozen and revived. No complex organism has survived cooling to temperatures that would halt biological processes. Even if suspended animation somehow became possible, the timescales involved create additional problems. Equipment fails over time, materials degrade, radiation accumulates in frozen tissue. Systems designed to operate for decades would need to function for millions of years without maintenance. The engineering challenges of maintaining any system across such timescales exceed anything humanity has ever attempted. Human genetic engineering might eventually enable enhanced radiation resistance, reduced bone loss, or other adaptations to spaceflight. Gene therapies could potentially modify human biology to better tolerate conditions outside Earth's protective environment. But transforming human biology to survive million-year space journeys would require changes so fundamental, so comprehensive, so far-reaching that the resulting beings might not qualify as human in any meaningful sense. They would be something new, something engineered rather than evolved. something designed for environments utterly unlike the African savanna, where human consciousness first emerged. They might be better suited for space travel, but they would not be us. The journey would begin with humans and end with something else entirely. The psychological challenges present equally insurmountable barriers, perhaps more insurmountable than the physical ones. Human minds evolved for social environments with regular interaction, meaningful activities, and perceivable progress toward goals. We are social primates who spent millions of years living in small groups, constantly communicating, constantly aware of our place in social hierarchies, constantly engaged with other minds. A journey lasting millions of years offers none of these psychological necessities. The destination would be so distant that no progress would be perceptible on human timescales. You could travel for an entire human lifespan, from birth to death, and be no measurably closer to Andromeda than when you started. The stars outside your window would not visibly change. The void would remain unchanged. The journey would feel like sitting still in darkness forever. Even if physical survival were somehow achieved through genetic engineering or suspended animation or technologies we cannot imagine, the mental health consequences of such prolonged isolation and monotony exceed anything psychology has ever studied. No human has ever experienced true isolation for more than a few months without severe psychological deterioration. Solitary confinement is considered torture precisely because human minds cannot tolerate extended separation from other human minds. Antarctic researchers isolated for winter months developed depression and cognitive impairment. Submarine crews on extended deployments require careful psychological monitoring. Astronauts on the International Space Station, in constant communication with Earth and surrounded by crewmates, still experience psychological challenges that require management. Projecting these effects across millions of years suggests psychological challenges that dwarf any engineering problem. The human mind is simply not built for journeys measured in geological time. We cannot maintain purpose across such durations. We cannot maintain sanity. We cannot maintain anything recognizably human about our psychology when isolated from the social environment that shaped our minds. Generation ships, often proposed as solutions for interstellar travel, face compounding problems when extended to intergalactic timescales. The concept imagines spacecraft large enough to support breeding populations, artificial worlds where generations live and die while the ship travels toward distant destinations. Parents raise children who raise their own children, maintaining some form of continuity across the decades or centuries required to reach nearby stars. This solution might work for journeys of a few hundred years to stars within a few dozen light-years, but a ship traveling to Andromeda for 2.5 million years would host approximately 125,000 human generations, assuming 20-year average generation times. 125,000 separate cohorts of people living, reproducing, and dying aboard a vessel crossing the intergalactic void. The social, political, and cultural changes across 125,000 generations defy any attempt at prediction. Human language changes beyond recognition over just 1,000 years. English speakers cannot understand texts written in their own language more than a millennium ago without specialized training. The language of Beowulf is as foreign to modern English speakers as German or Dutch. The language spoken aboard the generation ship after just 50 generations would be incomprehensible to the founders. Societies transform completely over mere centuries. Political systems rise and fall. Religions emerge and fade. Values shift dramatically from generation to generation. The social organization that launched the ship would bear no resemblance to the social organization that existed after even a tiny fraction of the journey. Revolutions would occur. Civil wars would erupt. Entire civilizations would rise and fall within the ship's hull. Maintaining any coherent mission purpose, any connection to the launching civilization, any understanding of why the journey began, across 125,000 generations appears impossible. The mission parameters would be forgotten within the first fraction of a percent of the journey. The travelers would retain no accurate information about Earth, about human history, about the original purpose of their voyage. Their mythology might include garbled references to an ancestral homeworld, but these legends would bear as much resemblance to actual Earth as our own myths bear to the historical events they dimly recall. The travelers who might eventually arrive at Andromeda would share no meaningful connection with the humans who launched the mission. They would have evolved culturally into something unrecognizable, speaking languages with no relationship to any earthly tongue, practicing religions invented aboard the ship, organized according to social structures that emerged from shipboard conditions rather than terrestrial history. They might also have evolved biologically. 2.5 million years represents significant evolutionary time. Our own ancestors 2.5 million years ago were Australopithecus, small-brained hominids who had not yet invented stone tools. The descendants arriving at Andromeda after such a journey might differ from current humans as much as we differ from those ancient ancestors. They would be aliens, descendants of Earth, but no more meaningfully connected to human history than we are connected to the bacteria that live in our digestive systems. This reveals perhaps the most profound barrier to reaching Andromeda, a barrier that persists even if every technical challenge could somehow be overcome. The humans who launched the mission and the beings who completed it would not be the same civilization. They would not share language, culture, biology, or any continuity of experience. The connection between departure and arrival would be purely genetic, a lineage preserved across millions of years but carrying no meaningful human content. The continuity of purpose, the shared cultural meaning, the connection to human experience that would justify such an enormous expenditure of resources, all would be lost across timescales that exceed any human institution's memory. Nothing humans have ever built has lasted more than a few thousand years. Our oldest continuous institutions measure their histories in millennia, not millions of years. The journey to Andromeda would require maintaining coherent purpose across durations that exceed human institutional capability by factors of thousands. What would be the purpose of such a journey? Not to expand humanity to Andromeda, because the travelers would not be human in any meaningful sense. They would be our descendants but not us, as different from current humans as we are from the first single-celled organisms. Not to satisfy human curiosity about Andromeda, because no human would live to see the results. The answers would arrive millions of years after the questions were forgotten. Not to advance human civilization, because human civilization would have transformed beyond recognition or ceased to exist entirely before the ship reached even a fraction of its journey. The journey to Andromeda, if somehow accomplished through technologies we cannot imagine and resources we cannot produce, would be meaningful only to beings so different from current humans that they might as well be alien species. The mission might continue from pure inertia, a tradition maintained for millions of years without any living memory of its original purpose, a ritual performed by creatures who have no idea why they perform it. This disconnection reveals something profound about human ambition and cosmic reality. Our dreams of reaching the stars emerge from a species whose entire existence measures barely 300,000 years. We imagine ourselves crossing millions of light years, while our own recorded history spans only 5,000 years. We think in generations, while the cosmos thinks in eons. We plan in decades, while the journey requires millions of years. The mismatch between human timescales and cosmic requirements is not a gap to be bridged, but an abyss that grows deeper with every level of analysis. The more carefully we examine what intergalactic travel would require, the more impossible it becomes, not just technologically but conceptually. We lack the cognitive framework to meaningfully plan across such durations. We lack the institutional capability to maintain purpose across such timescales. We lack the biological continuity to remain ourselves across such journeys. Yet even contemplating these barriers serves a purpose beyond merely cataloguing obstacles. Understanding why we cannot reach Andromeda reveals truths about our cosmic situation that inform how we might think about human existence and significance in a universe far larger than we can ever explore. The universe is not built for travel. The vast distances between galaxies, the cosmic speed limit embedded in space-time, the expanding space that carries destinations beyond reach, all suggest that cosmic geography keeps civilizations isolated by fundamental design. If design is even the right word for physics operating as physics must operate, each galaxy represents an island in an infinite ocean. The physics of that ocean, the distances involved, the speed limits imposed, the expansion occurring, prevents any voyage between islands within any reasonable time frame. We are marooned on our island, able to see distant shores but unable to reach them, separated by waters too deep and too wide for any ship to cross. This isolation may explain the famous Fermi paradox, the apparent contradiction between the high probability of extraterrestrial intelligence and the complete absence of evidence for such intelligence. If every civilization faces the same insurmountable barriers to intergalactic travel that we face, then advanced species throughout the universe might exist in permanent isolation, unable to contact neighbors in other galaxies, unable to confirm whether others exist, unable to break the cosmic silence that surrounds every inhabited world. The cosmos may be filled with intelligent life. Billions of civilizations might exist across the observable universe, each imprisoned within its own galaxy, contemplating the same stars we contemplate, wondering the same questions we wonder, facing the same insurmountable barriers we face. They look toward us across millions of light years. We look toward them, and the void between us ensures that we will never meet, never communicate, never confirm each other's existence. But there is another way to interpret these facts, a perspective that transforms cosmic imprisonment into cosmic meaning. The vastness that imprisons us is the same vastness that created us. The nuclear furnaces of stars forged the heavy elements in our bodies. The cosmic distances that separate galaxies allowed the billions of years necessary for biological evolution. The same physics that prevents our escape also enables our existence. We are not external to the cosmos, trapped within it against our will. We are expressions of the cosmos, matter configured into patterns capable of contemplating matter. We cannot reach Andromeda, but we can see it. We can measure its distance with extraordinary precision. We can calculate its composition from the spectrum of its light. We can predict its collision with our galaxy 4 billion years hence. We can understand why we cannot reach it, which is itself a form of reaching. The light from Andromeda that entered your eyes tonight carried information across 2.5 million years of void. Those ancient photons became electrical signals in your retina, patterns of neural activity in your brain, conscious experience of a distant galaxy. In that moment of observation, Andromeda was no longer entirely separate from Earth. It had become part of your mind, part of human knowledge, part of the cosmic story we are learning to tell. We may be prisoners of physics, confined to our local cosmic neighborhood for all of human existence. But we are prisoners who can see the entire prison. We are prisoners who can understand the walls that contain us. We are prisoners who can appreciate the vastness we can never traverse. Perhaps consciousness observing the universe, understanding the universe, appreciating the universe, serves a purpose that transcends physical travel. Andromeda hangs in the autumn sky tonight, 2.5 million light-years away, approaching but forever unreachable. 1 trillion stars burn in its spiral arms. Billions of planets orbit those stars. Perhaps some of those worlds harbor conscious beings who look toward our galaxy and wonder the same things we wonder, who feel the same cosmic loneliness we feel, who face the same insurmountable barriers we face. We will never meet them, but we can know they might exist. We can imagine their thoughts. We can recognize that consciousness, wherever it arises, faces the same cosmic constraints that imprison us all. The real reason we cannot reach Andromeda is not a single barrier, but an interlocking system of physical constraints that apply uniformly throughout the cosmos. Distance creates journey times exceeding any conceivable human duration. The speed of light prevents shortcuts that would compress these journeys. Cosmic expansion carries most of the universe beyond any possible reach. Human biology, psychology, and institutional memory cannot span the timescales involved. These barriers are not defects in the universe, they are the universe. Same physical laws that create galaxies, ignite stars, and enable life also separate those galaxies by insurmountable voids. We exist because physics operates as it does. Our confinement is the price we pay for existence itself. Look toward Andromeda tonight. See the light that left when your ancestors were learning to make tools. Contemplate the trillion stars you will never visit, the billions of worlds you will never explore, the possible civilizations you will never contact. Feel the cosmic loneliness of existence, isolated by incomprehensible distances. Then recognize the miracle of your awareness. Matter, configured into patterns capable of contemplating its own imprisonment. Physics that not only builds walls, but builds consciousness to recognize those walls. A universe that creates beings who can understand why they can never escape. The galaxy that cannot be reached remains the galaxy that can be known, and perhaps knowing is the only form of reaching that the universe permits.